Okay, and I'm glad you brought up minimal grounding set. Could you explain what that is? Because I find it very fascinating.
If you take a dictionary, and this is, I like to do this in words rather than showing you a diagram. If you take a dictionary uh, and you don't know, in a language that you don't know, this is at the same time an example of the symbol grounding problem. In a language that you don't know, like a Chinese dictionary, what you can do, don't ask me how, but what you can do is you can pronounce the characters. So somebody says, what does ban ma mean? And so you know how to, and you can alphabetize it. So you get through the dictionary, you reach the word ban ma, and what do you find? And ban ma is a set of Chinese characters. What do you find beside it in the definition? Another string of Chinese characters. You can pronounce them, and you can look them up again, but you're not getting anywhere. You're just going around in circles because you don't know what any of them mean. So the minimal grounding set is how many words and which ones do you need to know already uh, in order to be able to learn all the rest of them from words alone. Banma happens to mean zebra. So zebra, and the definition of zebra is a horse with stripes in Chinese, right? So how many words in the dictionary do you need so that all the rest of the words, besides those minimal words, you can reach just by words alone? And the surprising answer is it's somewhere between 750 and 1500, which is very few. I mean,
Mm-hmm.
dictionaries have hundreds of thousands of words, can have hundreds, if you, especially if you include technical stuff. Um, do you want me to tell you how you find that out? It's also simple.
Absolutely.
Okay, so what you do is in a dictionary, you can take all the words that are, by the way, what's a dictionary? Dictionary is a set of words in which every word in the dictionary is defined by words in a dictionary. And a definition is a string, it's a proposition, a string of words. And to simplify, it basically tells you the features of the defined word that define it. So with this definition of zebra is a black and white striped horse looking thing, right? That so in a dictionary, you have every word is defined, but not every word by a word in the dictionary, but not every word goes on to define anything else. There's some tail end, there's sort of not dead ends, but ends that go no further. The example I usually give is pterodactyl, which is a flying dinosaur. Maybe I'm wrong. I never even checked whether a dictionary contains a definition of something else. I don't have to because we use a computational method to find it. Does the word pterodactyl is it used to define something else? Are there green pterodactyls and blue pterodactyls, and we call the green pterodactyls with one name? I don't know, but there are things, lots and lots of words in the dictionary that don't define anything else. You can make a graph out of the dictionary where you take the word that is being defined as one node, and then all of the words that define it as incoming nodes defining that word. And and in that graph, you can see whether there are any words that get incoming nodes defining it, but they don't define anything else. And if you find one, you throw it out because you know you can get to it with what's left.
Mm.
And you keep doing that recursively. It's amazing. You can reduce the dictionary to about 10% of its size by removing all of these words already. But that 10% is still huge. It's not the minimal grounding set. It is a grounding set, but it's not the minimal grounding set. The minimal grounding set is within that dictionary. And I'm not going to bother you with any details over there. It's much smaller. You have to solve a problem called an NP complete problem, a problem that is almost, except under unusual circumstances, not soluble at all. For oriented graphs, it's called the minimal feedback, finding the minimal feedback vertex set. You can't do that computationally, but you can approximate it with a few tricks that are not important for what you're saying. And we found that for all of the dictionaries that we tested, that we could find the size. I'm not really, you'll see why I don't want particularly the set, but the size. We can find the minimal size by graph theoretic analysis and computation. And then it turns out that's the good news. You can find it, and it's very small, somewhere between 750 and 1500, depending on the dictionary. But the bad news is that there are many of them, all in that first reduction is called the nucleus of the dictionary, 10% of the dictionary. They're all in the dictionary, and there are other structures in there which I won't bother you with, but there are many of them. Some of them are almost the same, just a few word differences, and some of them are more different. And so there's no point looking for the unique universal set of words that everybody has learned, and then everybody else did the rest of it in a dark room. They all learn different categories, a lot more than they really need for a minimal grounding set. But once you have a minimal grounding set, formally and logically, you can explain all the rest of the categories verbally. You don't have to do any more direct grounding.
Okay, awesome. Thank you for that explanation. It was really well done. How did you actually get a hint of how to like actually go into this direction of reducing the dictionary to this minimal set?
Well, actually, it was bumbling all the way. There was supposedly a dictionary called the Longman's Dictionary of English that had already done this analysis. It said this dictionary is for new learners of English, and every word is defined with just 2,000 control words. And we had a team of mathematicians and graph theoreticians get together, and we wanted to create the graph of that and then look at the structure of meaning, etc. But the mathematicians got disgusted right away. They said, this dictionary is not following its own rules. It's not, first of all, it's not a dictionary. It contains words that are not defined. Second of all, the control vocabulary doesn't define everything, and nothing in that control vocabulary is defined. So everything was wrong. But the mathematicians said, but we can make something true that is like that. And the method I described to you is the one that was used. We'll get rid of, we can obviously get rid of the words that don't define any other words, and that shrinks it. And then we'll try to find the smallest one. And then we did that with graph theory. I was a non-mathematician. They were doing all the technical stuff.
Okay.
And
And how
then,
long?
and then we found out that the words in the minimal grounding set are learned, are first of all, more frequent in the language, significantly more frequent than other words, much more frequent. Second of all, are learned younger, so that fits with the fact that they're grounding words. But the correlations are not huge. I mean, there's a huge number of words there, and finally, there's some relation to whether the word is concrete or abstract, whether it's this apple Charlie in my hand, or apples, or fruits, or edible things, or objects. That hierarchy has something to do with it, but it's not clear yet what.